Next on stage, I'd like to invite Vivek Bhole from Vivek Bhole Architects. Vivek is considered as one of the leading architects in Mumbai and has made his mark on the skyline as a result of his hard work and architectural designs. His team comprises of more than 200 highly talented architects, interior designers, engineers, and other professionals. And Vivek boasts of an office of nearly 50,000 square feet in one of the prime areas in MIDC Andheri. With over 15 years of design experience, Vivek provides the firm with senior leadership and design talent. Vivek is again going to talk about something very interesting today. Over to you, Vivek.
Thank you, Carl. So this is my favorite topic. For past few years, I'm only talking about parametrics because since morning I'm attending these lectures and everybody is going into those technical intricacies and those charts. But then when it comes to giving the work, we see that foreigners are preferred only because they have adopted the technology much before of us. And what they are producing is not with the conventional technologies we are still using, but with something totally different. So in one of such event in abroad, I witnessed the first presentation on parametric, and that motivated me to self-learn the topic. So I did my experiments in past 6 years. I have achieved something, not everything, but in all my lectures, I try to present parametric so that the next generation and all of us, we should start doing it today so that after 10 years probably, we'll be able to compete with the world. So the parametric architecture or digital architecture, what is it? It is just a... Girish, you have to give the lecture. Huh? Okay. So this is a sequence of loops and conditions, and actually we generate the form or we generate the drawing which is unimaginable, undraftable, and which is unimaginable or undraftable. You cannot construct it on site. So you can really create very complex geometries. Parametric geometry can be used in architecture, interior design, everything, fashion design, landscape architecture, in every art form. So let's say from where it is generated. Nature has got parametric design. So what we call as biomimicry. So something of that sort is something what is parametric is. You can see these are few examples what we see in nature. Now why we do parametric? Because as I said, we can create organics and complex shapes by various form finding methods. Now when we say form finding methods, like in parametric softwares, there are different tools and the things we cannot imagine. These tools help you to find the form which suits to your requirement. You can rationalize these forms and then depending upon the requirement, the material restrictions, their properties, we can actually rationalize the whole build form. We can do the interactive structural analysis. We can do optimization in different environmental simulations. And then finally, as Jay was saying, final output is always the shop drawing which is directly fired to the CNC machine. I have come to a conclusion that whatever you do on parametric softwares, unless you use technology even for the construction, the execution, with the use of these CNC machines, you cannot actually execute them the way you want. Now there are different softwares. Like I started with very basic software that was we called Revit. I started using Revit in 2006, and the day they introduced a plugin for that, we started with that. But then a powerful software called EcoSim and generative component, we also tried that. Revit and Dynamo was my first experiment. Then finally we stick to Rhino and Grasshopper. So most of my study, most of my experiments are onto this platform. Now when we talk about high-rise structures, uh, where are we using parametric designs? So in structural system we can use it, in facades we can use it, and we can also use it in composite way in structural facades. So the first is form finding, basic analysis of that form, various simulations what you can do on it, connectivity of these parametric softwares with other softwares, and then finally the output. In facades, there are different types, we'll discuss on that. And then structural facades like exoskeleton, space trusses, membranes, and then dynamic structures. Now these are very futuristic. We need not go into that futuristic approach, but then any architectural design, you can use digital platforms like these parametric softwares, and you can come up with something which is very different. So everything starts with form conceptualization. We use various softwares for even form conceptualizations, but then, can you please put it on? Put it that way. So basically when we use this software, let's say Grasshopper and Revit, Revit has got number of plugins, and also Grasshopper has got number of plugins. So I'm using almost like 80 plugins for Grasshopper, and few plugins for even Revit, for this Rhino. So when we start designing onto any structure, the algorithm, the parametric softwares give you full flexibility where you can actually decide onto the final product at very beginning stage. In general system, where we start with the basic 2D drawing and reach to the 3D drawing, here the whole process starts with 3D and ends to the 2D drawing. So for example here, if I make one single definition of algorithm, by just flick of a button, I can see the result where I got 5 supports, 4 supports, or 3 supports, and I can check, putting onto various checks onto it, I can see the possibility, the rationality of that structure. This is my one of the most favorite plugin. That plugin is called T-Spline, basically Autodesk plugin, and it runs in Rhino. And most of these buildings which are designed by international architects, in their presentations in abroad, they have talked about this plugin, so we started exploring that. And it's like clay molding, and you can create a form. Unfortunately, in the latest versions, because Autodesk is a different software company, and Rhino is a different one, so they stopped supporting the new versions. You can do the structural design of these structures even before you complete the design. So these are a few plugins. Like we use Kangaroo physics engine for smaller structures, and we also tried a plugin called Karamba. Now we want structural engineers to explore this further, because eventually most of the architectural firms are going to shift onto these softwares, and plugins like this can help them a lot. So you can see in the plugin, when we simulate, each and every node's displacement is measured, it is given, and depending upon the structure's characteristic and its properties, we can decide whether the structure is going to stand stable or not. And when I said interactive, you can see on the right hand side, it is giving me the form, and it is showing me in color the stresses, so that while designing the form itself, I can actually check the stresses, and I can design, I can fix onto the form So that is what is interactive form finding method. Then there are different environmental simulations. These are the plugins which are available in Grasshopper. So we mostly use Honeybug, Ladybug and Honeybee. So these softwares, they do various shadow analysis and this solar control and radiation control and even fluid mechanics. So something like this can be done in Honeybee and Ladybug simulation, where it is actually showing the reflection of the light which is falling onto the plaza in between two buildings. Then you can do different simulations with Honeybug, including this light penetration inside the building. The daylight factor you can actually see. And the best part of that is Honeybug can connect your Rhino and Grasshopper with various other softwares. So it supports different platforms like Daysim, Energy Plus, Open Studio, Radiance, and it's a to and fro kind of connectivity. And you can connect this with your Rhino, and you can do it interactively. So with one more plugin called Butterfly, you can also do simulations for wind and also something like tsunami. So you can actually check how the whole city is going to behave in case of tsunami. So when we say form rationalization, the first is always depending upon the material, the sizes available. You can always write the algorithm to check the viability of your design. Then you can optimize your structure by structural design, as I showed you. You can check its structural stability, you can check its facade simulations, and eventually, depending upon the machine which you are going to use for your final production, its characteristics, its limitations, you can utilize into your algorithm. And then this is little older subject where we wanted to connect our parametric softwares to building information modeling. We used to use software called Geometry Gym, and it used to connect Grasshopper with Revit, and we're getting the output in Revit directly. But now with the latest available softwares, there is a very good combination. There is a direct connection between ArchiCAD, Rhino and Grasshopper, and there is it's kind of interconnectivity between these softwares. So this was from structure point of view. When it comes to facade, when we go for a high-rise building, I'll take you through a very fast journey of this because facade is a different subject altogether. And last time I tried to give the lecture, it was like 1 hour lecture. So when I say seed-based facades, so you can always start with something like a number, a surface or a line or just collection of points to start with your definition of algorithm, and you can develop a geometry. So here in this case, we have got two sets of points. Automatically they get connected through algorithm, through lines, and see the end result. Finally the end result is those geometries. Now if you change those seeds, if you change the set of these points, the result will be something different. So in all these algorithm and parametric subjects, you don't really draft a drawing, but you write the definition of the aesthetics. And then once you change the seed, you will get different output altogether. So here I have used one definition on different surfaces. So variety of these surfaces are there, and see the results. Here, if you want the same into facade, like you take one geometry, you write a definition, here surface is the seed, you change the surface, you will get different result. You can use geometry as a seed, here I have taken just one this this block, and then randomly the points are generated inside, and there is something called as Verneuil pattern. It gets generated. Now if I give, instead of this block, if I give a sphere as a seed, it will give me a different result altogether. Here it's a combination of two different seeds. One seed is these two lines, the other seed is a geometry which is there at the lower part of the slide. So that X which is given to the surface which is formed by those two lines, and see the end result. Suppose instead of that X I use any other seed, I'll get different result. Now when I want to make it little more complex, so what I do, I give some variables to this subject. So different variables, like you used to do X and Y. If I give X and Y variables, and we connect these X and Y variables with the location of that particular surface, possibly we'll get different iterations. So with the same one definition of aesthetics, I can generate number of those iterations, and how I can help, how I can use that into my design. So these are different set of iterations. Same geometry with some variation gives me something different, and when I put it onto one surface, now instead of a simple seed, I am using a variable seed. That variable seed will give me something like this. So we call them attractors. Now here there is a curve which is visible. So that curve was one of the attractor. Depending upon the location of individual member in respective of that curve, it is giving me a different iteration, different alternative of that geometry. And that is how I am forming this complex shape. These are few examples. So we always know they look nice, but how we make them, so that was the basic of it. We can use them on high-rise buildings. Now this way you can make very monotonous facade into very interesting looking facade. So you can use even an image. Image can be your seed. You supply a image, any image to your algorithm, and it will, depending upon the image, the intensity, the brightness, or the color hue, you can actually give a different geometry to your facade. Even something like this, where you are using that for projections instead of perforations, or something like this, where you can actually bring some triangulation with the help of some geometry. And then there are these complex kind of facades where you can see they are changing their shapes, they are reducing and increasing the openings depending upon the requirement from weather and climatic conditions. And these are environmentally responsive facades. And it is proved that they give a lot of saving into your energy consumption. So there are few more examples like this, where you can see those fins closing down and opening and controlling the light inside. Or something like this, where the facade is moving. So these are basically dynamic facades. Now when it comes to a composite of facade and a structural system, the most popular today is die-grid. So we saw in Carl's presentation that most of the time in abroad, they have got a central core and peripheral columns. So instead of just having simple peripheral columns, there is a technique where you can actually use a skin developed with parametric softwares in a die-grid fashion. So these are few examples, and this is getting a lot of popularity in abroad, even in India. Like now somebody is quoting that the first parametric die-grid facade there in Hyderabad, those 4 towers coming up. I don't know whether Carl's firm is involved in that, but Sir Norman Foster is he's there. These are few more examples. The CCTV tower, there are different variants of this diagrid. This is the excessive use of the technology. So we went to visit this structure in one of the CTBH conference. After it was over, we saw this presentation in CTBH and we decided to see this building. We went there and we thought this is really ugly. But then it is something they have achieved with a lot of efforts. I don't think the efforts were worthwhile, but then the building is unique. The other way where you can actually use parametric softwares for form findings are space trucks. So in space trusses, you can evolve a form and you can do number of iterations. Like Jay was explaining in his previous presentation, with a seed, you can develop almost like 10,000 options. He took 10 days, but actually the software takes only 1 minute. So you can generate 10,000 options in 1 minute, and then you can select one out of them. So these are some examples. A space truss, a complex form can be developed. You can use membranes for structural facades. So this is age-old example. The first of its kind, I think this was the first tower they built, 50-story plus in Dubai. And finally, the boldest experiment what they did is this rotating tower. And because of that parametric shape of that software, it is not just evolved as parametric as a design, but it is going to change all around the clock. The whole process of these parametric softwares and the development through parametric softwares is like this: material selection, form conceptualization. We can do those simulations, we can do rationalizations, we can do the structural design before actually giving it to the structural engineer. You can do the basic stability of it. Then you can take it to BIM so that you can generate detailed drawings. And then drawing for machines are always the byproduct of these softwares. These are few projects which we are experimenting. So we tried first parametric use in one of my projects, that is Vanavigna Park. So we designed its crown with this parametric, and then that whole structure is like 12-meter tall steel structure from the terrace level. And you can imagine this is the 61-storied building, the tallest residential occupied building in the city, and this was to be erected on top of it. So we calculated each and every joint through the software, and now it is complete, already occupied as well. Now we are doing this one more building. This is in diagrid. So this is supposed to be the tallest and the biggest building, commercial building in Mumbai. Already the work is allotted. Tata Projects are the contractors for this, and we did the whole design on algorithm, including each and every panel, each and every mullion was designed. And as I said, the exoskeleton is the next popular subject that is going to be there in India as well. And this is a next project which we are going to do. And this is supposed to be taller than Eiffel Tower, 30 meters taller than Eiffel Tower, somewhere in Gujarat, I cannot tell you where. But this we are doing for Steel Authority of India. When they announce it, we are at the finalization stage of the design. And I'll invite Girish to explain the next slides. These are your slides. Hope you know them.
So Vivek approached me with this unique project and SAIL, as he said, SAIL, Steel Authority of India, wanted to build a building in steel. And somewhere, now he is talking of Gujarat, but when he approached me, the location was not finalized. So, as a structural engineer, we get into the, that rut of earthquake zone and wind zone and what is all that kind of stuff, what is the soil parameter. But when he explained to me how he has come up with the concept of the shape and how he has come up with the facade, then I said, okay, let's take a back seat. The structural design is not important. It's going to happen. In fact, I don't have to do any structural drawings, correct? Because this is one kind of building where the form itself, the facade itself is so much structural. It's going to be self-supporting building, and whatever I do is just just put it on paper or in some kind of software, give a file to the contractor who will CNC the facade elements and fabricate them. This is all we are going to do. So, as regards the location-based parameters like earthquake and wind, I'm sure the software itself, when he says the structural design will happen in the initial stages itself, when he's making the form of the building, all those input parameters can be fed into that software itself. Everything will be confirmed, and in this geometry, the geometry itself is self-stabilizing. It's a tapering building. So as a overall form, there is no much structural challenge here. The problem will lie only with the load flow. The gravity and the lateral loads have to reach the foundations, and the grid system that is followed here is excellent way of transferring the forces to the foundation. So there is no problem. But to be on safer side, we both decided that let us have a central core as well. In any case, which was required because there is a restaurant on top of the building, you can see here. So you have to reach that place. In any case, you will need to have vertical transportation. So the cores required for vertical transportation themselves will add to some kind of stability. So there was some other discussion regarding how to make this form integral. And instead of having a cantilevered restaurant, we decided to just have the form itself take the shape. And you can see the highlighted portion where the form has been curved to create that bulb kind of thing which houses the restaurant. So that adds, the solidity to the geometry. And you see here, although the title of the slide is Fabrication and Direction, I don't believe anybody is going to have fabrication drawings to make this kind of stuff work. Every star-shaped panel will be of different dimension because the building is tapering, the number of stars are changing. So this is going to be completely automated fabrication, and which is possible nowadays. We have been doing some buildings, very complex buildings, where it's not possible to draw fabrication drawings. And everything will be given in the form of algorithm files to the contractor, and the CNC machine will take the inputs and start cutting the plates, the members, and even the welding will be done automatically. So major parameters, of course, will be wind and all that. It will be taken care of. We have designed this building for the entire range, 44 meter per second to 74 meter per second. Probably RWDI will get this project very soon to have it tested in wind tunnel. That's it. I think earthquake zone, again, I said it was not decided where the building was located. In any case, this form is so stable, I'm sure I can build it in any zone, earthquake zone in India. And What will change is maybe the plate thickness of the star here and there, but it's going to be absolutely fantastic. Most important aspect of this building, however, will be the foundation. This is going to be more than 300 meter tall building. What is the exact height? About 300 meters. So the toppling effect is the only thing that I have to tackle at the foundation level. And the wind-induced toppling has to be resisted by a mass at the base. Remember, this is a steel building. The building itself will have very small mass compared to its volume. So earthquake is not all that important factor, but the wind is. And I have to create a massive foundation to stabilize the building. And probably that will be the toughest challenge, because even our concrete technology is not all that advanced as our steel cutting technology is. So I think that will be the major challenge. Probably we'll have to go for some kind of tension piles somewhere, or pre-stressed rock anchors to hold the foundation pinned to the ground. The spire is the most important aspect of this building. That itself is, I think, about 75 to 100 meter tall, and there is bound to be some kind of flutter or high accelerations in that part of the structure. This building, however, is going to be occupied at the restaurant level by human beings. So it is very, very necessary to control the accelerations in the building. We cannot just wish away that it's a monumental building, not going to be occupied, but it's going to be a restaurant. There will be a lot of wine glasses and cutlery and all that. We should not start flying off here and there when people are going to be there. So controlling accelerations will be very important, and for that, that spire is it has a very small planned dimension, and only some kind of viscoelastic dampers only can take care of the acceleration. So I think a lot of damping will be required to this building, because again the building doesn't have its own intrinsic mass. So there has to be supplementary damping in this building. So all these things have been already preconceived, and we'll be going through all these pre-designed studies, material testing, wind tunnel, and site-specific seismic studies and all that. And all these preventive measures we have already thought. So you want to add something to this architecturally?
This is the final picture which we are going to see someday. If it happens, it will be 30 meters taller than your Eiffel Tower. And thank you.